This is the screencast for section 3.4, example 3. So again, we've got tons of terminology and different things we have to pick up from graphs and their functions and data points, etc. So I, over the next 2 pages of your notes, have kind of given you a definition, maybe a little formula, and a visual of what's going on. And I put this line down the middle to show you what's happening versus when the graph is going up versus going down, depending on what we're looking at here. And throughout this section and maybe even further sections, I'm going to come back to different pieces of this page of your notes. So make sure this page in your notes is earmarked. Right now, we need to worry about, and don't worry, but velocity. Velocity is directional. All right, so velocity is a rate of change, and you know that, but when velocity is positive, the object is moving forward. When velocity is negative, the object is moving backward. So if you look at this graph of velocity here, though the line is going down, this is not a position. This is a velocity. So your object is traveling at, let's say, 10 miles an hour, 9 miles an hour, 8 miles an hour, 7 miles an hour. So it's slowing down. That's what this is. That's why it's going down. But it is still moving away. It's moving forward. Okay. So now let's look at an example where this might apply. Example 3, reading the velocity graph. A student walks in front of a motion detector that records her velocity at 1-second intervals for 36 seconds. She stores the data in her graphing calculator and uses it to generate the time velocity graph shown in this figure. Describe her motion as a function of time by reading the velocity graph. When is her speed a maximum? Okay, so there's 2 things we're being asked to do. First, describe her motion. I don't really like those describe the motion questions. They're intimidating. Describe is a very vague word. Well, I'm going to hopefully help you and how to narrow down your explanations. So first, what I do, if I have to describe motion, I am talking about the object's velocity, and I need to keep that in mind. So I am putting down the word velocity at the top of this graph. This is the derivative of position. This is velocity v of t. It is a rate of change. The bottom, the x-axis here, is going to be measured in seconds. The y-axis is going to be measured in, well, actually it doesn't tell you what it's going to be measured in, so we're going to say feet per second. So the velocity at a certain time. So for example here, at 1 second, the object is traveling, or this girl, 1, 2, 3, 4, is traveling about 4.5 feet per second at 1 second. Okay. Now the next trick I use to describe motion is I break it up into parts. I break this graph up into parts where the velocity has some sort of change that's happening. So between 0 and 1 second would be my first part that I'm looking at. So this 0 to 1 second. Between 0 and 1 second, this girl's velocity is increasing. She's at 0 feet per second, 1 feet per second, 2 feet per second, 3 feet per second, 4 feet. So she's getting faster. Now remember, velocity is also directional, so I can say that she is also moving forward. She is at a positive velocity, so she's moving forward. Now my next break, it looks like this little plateau here, so I'm going to call that seconds 1 to 2. Now 1 to 2 seconds, she is not standing still. You are not looking at the position graph. This is a velocity. She is maintaining about 4.5 feet per second, so she's walking at a constant pace here. So for 1 to 2 seconds, she is still moving forward, just at a constant velocity. Now the next break in the graph looks like it's going to come from after that plateau to maybe that 0. So to me that looks like 2 to 3.5 seconds. So between 2 and 3.5 seconds, she's still moving forward. She is still at a positive velocity. Her velocity is above the x-axis. However, she is slowing down. She's like at 4 feet per second, 3 feet per second, 2 feet per second, 1 feet per second. You get the idea. Now the next piece of the graph where no significant changes take place are probably to this minimum. So I'm going to call that 3.5 to 5 seconds. Between 3.5 to 5 seconds, she has now changed direction. She's going backwards and she's getting faster. she's at like -1 feet per second, -2, -3, -4, -5, all the way down to about -7 feet per second. Now it's tricky to say that her velocity is getting faster because her velocity is getting faster is true. You just can't say that her velocity is increasing because the graph of velocity here is decreasing. Now the next break in the graph comes from the minimum probably to where she hits, the velocity hits the x-axis there. So I'll call that from 5 to 6.5 seconds. From 5 to 6.5 seconds, she is still moving backwards, but her velocity is slowing down. Now next will be this plateau here on the x-axis. Her velocity is at 0 for 1.5 seconds. Between 6.5 and 8 seconds, she is stopped. And then the last bit from 8 to 9 seconds is very similar between 1 and 2 seconds. Her velocity is increasing. She's getting faster and now she's back moving forward again. Now something I want to mention here is at this spot, this 5 seconds, at this 3.5 seconds, she stopped for an instant, like just 1 instant to change directions. You probably didn't even see it. She just turned directions and that forced her to stop for an instant. So now let's answer the question. When is her speed a minimum? Well, speed is the absolute value of velocity. So here's our velocity graph in my little example. Speed is the absolute value, so all negative y values are going to become positive y values. We have a partial reflection over the x-axis there. So I can mock that on our graph by taking this dip underneath the x-axis and going all the way up there. Definitely looks like her fastest speed is going to be at approximately 5 seconds. And her velocity at that 5 seconds, or her speed, excuse me, would be a positive 7 feet per second. Then now try problem number 9. Says that the accompanying figure shows the velocity, or v, of the particle moving on a coordinate line. So we've got a particle that's moving back and forth. So we want to not describe its motion like we did in the last problem, but we've got more specific questions, which is good. So part A, when does the particle move forward, move backward, speed up, and slow down? Well, forward is when the velocity is positive, which will occur between seconds 0 and 1, not including 1, because at 1 the particle is stopped for an instant. Then again from 5 to 7. Now I guess you could have included 0 in your notation, so that would have been fine in your interval. The particle is moving backwards between 1 and 5, so that's when the velocity is negative. Now this particle is going to speed up when the velocity is going away from the x-axis. Remember, the velocity is 0 at the x-axis, so the farther away you go from 0, the faster the object's going. It's just if it goes faster in the upwards direction, we're going forward. In the downward direction, we're going backwards. So the object is going to speed up when the velocity goes away from the x-axis. And that occurs, let's see, from 1 to 2, from 5 to 6. Then the reverse happens for when the particle slows down. The particle is going to slow down when the velocity approaches the x-axis. So 10 feet per second, 9 feet per second, 8 feet per second, etc. Or same thing here, -10, -9, -8, -7, approaching 0. So when the velocity approaches the x-axis, the object is slowing down, and that occurs between 0 and 1, and 3 and 5, and again from 6 to 7. Now the question is, question B is, when is the particle's acceleration positive, negative, and 0? Okay, wait a second. The acceleration is the derivative of velocity. So acceleration are the slopes of the secants or tangents in the velocity curve. So if the slopes are positive, the acceleration will be positive. If the slopes are negative, the acceleration will be negative. Well, what causes positive and negative slopes? Let's see, positive slopes are caused by an increasing graph. So let's take a look at that. When the particle's acceleration is positive, the velocity is increasing. So if the velocity is increasing, the acceleration is going to be positive. So think about derivatives and slopes here. These slopes are negative, these slopes are positive, so the acceleration will be positive between 3 and 6. Negative acceleration is going to occur when the velocity is decreasing. The velocity graph is decreasing. And that occurs between 0 and 2 seconds, and then again at 6 and 7 seconds. Now the acceleration is 0 when the velocity curve is neither increasing or decreasing, but is constant. That will have a slope of 0. So that happens between 2 and 3 seconds and 7 and 9 seconds. Part C asks, when does the particle move at its greatest speed? Ooh, speed again. Okay, I actually just took a bobby pin from my hair, measured this, and then drew it equivalent up there. It looks like we have two different places that the particle is moving at its greatest speed. That would be at 0 seconds and then from 2 to 3 seconds. Now part D, when does the particle stand still for more than an instant? Okay, well, the particle stands still for only an instant right here at 1, at x equals 1, when it's changing directions. But the particle is still for more than an instant, let's see, when the velocity is 0. So that's not this. This is when if distance wasn't changing. If this were the distance graph, then yes, the particle would be standing still. Remember, this velocity is still like negative 10 feet per second. We're looking at a velocity of 0, and that's between 7 and 9 seconds.